All right, so guys, if you'll look at this, yes, sir. Yeah, if you'll get one of those, they're up here on the cart. Okay, get both of these worksheets. Now, if you will notice what I wrote on this is very important because the problem is this is what's going to be a lot of what's on the new version of the AP exam. So you have to go through this to be able to figure out what you're going to be looking for. Okay. Now, if you'll notice part A, what's it say? Explain. That's very vital to your comprehension and your understanding of what you need to do. So you have to use words to explain with us. That's what the arrow says. Explain how to prepare. So you have to use words. Now, what else does it also say in this part? Include appropriate calculations. Right there. So when it says calculations, does that mean math? Yeah. Yes, that means math. So explain how to prepare a 100 milliliters of a 0.1 molar Ki solution. What is the first thing we're going to have to do to figure this out? Got to find grams. Why? Very good. You need to find out how much of this solid you're going to have. Now notice what it has. It has what? Ki crystal. What state of matter is a crystal? It's a solid, so you got to figure out how much it is. Now, appropriate calculations would include getting to grams. How are we going to get to grams? Very good. Now, so I need moles, and I need molarity times volume, right? Okay. Now, is this an appropriate calculation? Absolutely. So 1.0 molar times, now, can I leave that in 100 milliliters? No. So 0.100 liters. So how many moles is that? Thank you. So 0.100 moles of Ki. Now, I need what? Grams. Very good. So I'm going to need grams next. So when I go from moles to grams, did anybody solve for the molar mass of Ki? Very good. 166.01 grams. So that will have given you 16.6 grams of Ki. That's what you need first. So 16.6 grams of potassium iodide solid. So the key here again is we've included appropriate calculations. So if you did not include this calculation, you can't tell me how to do this properly. So to find the appropriate mass, we did molarity times volume and then converted it to grams. Guys, every bit of this is in your chapter 1 or chapter 4 part 1 notes. Go back. Every bit of this is in here. I went through and I did this several times. Okay. So now let's go in and let's explain what we got to do. What's wrong? 0.100. This right here is 0.100. And it's 16.01, so 16.6 grams of Ki. Now, so this is our explanation. What are we going to do with that 16 grams? Okay. Well, the first thing we need to do is mass out, not of, mass out 16.6 grams of potassium iodide crystals. Now, could you even go a step farther and include this? Could you even go that far? Sure. I mean, if you want to be as accurate as possible, yes, technically that's how you would do it. Okay. After we have the mass of 16.6 grams, what do we do next? Very good. Now, why am I putting it in a 100 milliliter flask, first of all? That's exactly what the amount we needed. Now, why is it volumetric? What's wrong? Why is it volumetric? That's the what? No, you're exactly right. Because you remember, we have a beaker. This is a beaker. Difficult, right? Then we have an Erlenmeyer flask, which is like this. And then the volumetric flask is kind of like this, and it's got that line, right? This is why we use the volumetric flask. That's not what I want. Okay, next. Place in a 100 milliliter volumetric flask and do what? Very good. And add 50 milliliters of hot distilled H2O. Now, two things. Why am I putting in a certain amount of water? To dissolve it. Why am I putting in hot distilled? Okay, I'm gonna get to that. Okay, why is it hot? Dissolves faster. If you're making sweet tea, do you use hot water or cold water? Hot water. Who's making cold water sweet tea? Anyways, it's hot water because it makes it dissolve faster. Why is it distilled? It's pure. Like if I take tap water, is it just H2O? No, it's got a bunch of other stuff. We don't need all that. So it's 50 milliliters of hot distilled water. Now, the question Janasia asked is why is it 50 milliliters? Okay, if I put in 1 milliliter, is it going to dissolve all that? No. If I put in 100 milliliters, that's filling it up. We don't want to fill it up, right? Okay. And this is something that I did not talk about last time. So if you've already written this answer, you may want to add this in because this is very important. Add 50 milliliters of hot distilled water. And here's the next two key parts. And swirl to. And this is the part that I left out last time. There's two S's in there, right? I would say, you could say stir is fine. Stir is perfectly fine. But the key is to do what? Completely dissolve. Because if you don't completely dissolve it, is it going to be the correct concentration? No. You have to completely dissolve it. Now, based on our solubility rules, is Ki 100% soluble? K is a group. All group 1s are. So that will not stay a solid once you put it in. So, place in a 100 milliliter volumetric flask, add 50 milliliters of hot distilled water, and swirl to completely dissolve. Then what? Very good. So, well, you could really say, then fill the flask up, to the 100 milliliter mark, and you're done. Again, I promise you're going to see this. I guarantee it. You have to know. You better be able to know how to do this. Okay. So the key here is the mass. The digital balance. Yeah, that's good and all. It's not going to kill you. Make sure you tell me how big of a flask you need. Make sure you tell me how much water. Make sure it doesn't necessarily have to be hot, but it has to be distilled. You have to swirl and completely dissolve, and then you have to fill to the mark. Okay, so those are really the important things. 100 milliliter volumetric. So again, those are things that you really, really, really have to grasp in this. Now, let me show you what the key said and how you would have earned points here. Okay, here's what the key says. I need to pause the video so I can get the live feed in. Okay, so this time we have, let's see, this is where it is. We are preparing, now this drives me nuts. We are preparing 1/10 of a liter. Why'd they do that? What is 1/10 of a liter? 100 milliliters. I don't know why they did this. This really drives me nuts, but then guess what? Those smart, intelligent chemistry people wrote that grammatically incorrect. Idiots. Okay. What? That's why they're chemistry people. We don't know how to do English, but we know what this means. All right, but again, so this is really the answer they were looking for. So as long as you got this, you're fine. Therefore, mass out 16.60, that appropriate? Grams of Ki on a balance. So is that what we have pretty much so far? Yeah. And place it into a 100 milliliter volumetric flask. Those are keys, right? With approximately 50 milliliters of deionized. Now, isn't deionized and distilled the exact same thing? Okay, no difference. 50 milliliters of deionized water. Then, this is where I told you the kicker was. Swirl until what? Completely dissolved. Then, fill the volumetric flask to what? Is that not almost exactly what we wrote? Now, I'm being honest. Earlier, I printed this out, did not even look at it. Second period, I wrote everything except for the completely dissolved part. So if you will follow the standard of what I've set forth, guys, it will always fill in. The only thing that's going to change every single time you do it is the mass, the compound, the size of the volumetric flask. That's it. That's the only thing that's ever going to change. And maybe that, depending on how much mass you have. So that is the only difference. Any questions on this? Guys, if you don't know how to do this, it's all in your notes. Go back and look at it. Now, let's go to the next question. All right, so part B. In the space provided below, show the interactions of the components of Ki aqueous. Now, as soon as it says aqueous, what is that telling me? Hold on. Okay. As soon as you see aqueous, Stakeesh, you said it. What does that mean? Perfect. That's exactly right. You have ions in solution. So are you going to have some pluses and some minuses? Yes. By making a drawing that represents the different particles present in the solution. Guys, this is exactly where the AP Chem exam is going. I guarantee you're going to have to draw something or explain something on the exam, no doubt about it. Because what they're wanting to try to do is see if you understand. When I have a beaker of something or a flask of something, what's going on in there? If I could actually take a microscope and look inside of it, what's going on? How are they interacting? Not necessarily the math. They want to see if you understand what's going on chemical-wise as it's mixing. All right. Base the particles in your drawing on the particles represented above. Guys, that's really important. Base the particles in your drawing on the particles shown in the representations above. So do you think you're going to have to kind of use something like this? Yes. Now, first and foremost, this is the biggest difference. What state is this in? This is in aqueous. So what are we going to have to do to this crystal? We're going to have to break it apart. So this is the first thing you need to realize of how to do. It's going to break into K plus and what? I minus. We understand this, right? The biggest thing that people in first period did not understand is which one is which. Okay, well, let's talk about why. Potassium's atomic number. Can anybody tell me what it is? 19. What about iodine? Which one is much bigger? So which one's the bigger dot? Iodine, right? Does that kind of make sense? So I is going to be that bigger one. That's normally going to be the case some of the times, not all the time, but normally the cation is going to be a little bit smaller. Okay, but this is true. So that's what's going to happen. Now, here's the instructions. Include only one formula unit of Ki and no more. So we want 1 Ki and no more than 10 molecules of water. Okay. Now, are we going to draw one crystal structure or one potassium ion and one iodine ion? We're wanting ions, right? So we need 1 K plus and 1 I minus. So you kind of understanding what the instructions are? And then how many water molecules? No more than 10. So if we put 6, are we fine? Yeah, if we put 8, we're okay. Your drawing must include the following. And here's the biggest deal. Identity of ions, symbols, and charge. Isn't that what this is? We're good there. We just have to draw it with the little circles around it. And number 2, This is where every one of you probably would have failed this, is because you didn't know what to do here. And when you see it, you're going to be like, I would have gotten that if I would have just known what it meant. The arrangement and, here's the key, proper orientation of the particles in the solution. Proper orientation. What does orientation mean? The way it's presented, how it's arranged, right? So let's look at this. All right, so we've already said that K is going to be the little one, right? And what was going to be the big one? Now, does it really matter that they're that different? No, but at least try to make them different. At least try to represent the structures. Any questions here now? So, have we just done the identity of the atoms, symbol, and charge? Yes. Now, what did it say up there? It show at least how many formula units of Ki? This is all we needed, right? Now we need to show the water molecules. This is where your intelligence has to kick in. We know that this is going to be surrounded by water, but how is it going to be surrounded by water? Very, 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 very good, Stakeesh. How many times have I drawn this in this class? I said you got water like this, and you got this going on, right? How many times have I done this? Way too many. This is how we now need to approach this. And how many times have I said that the hydrogen is a slightly what? Slightly positive, and oxygen is slightly negative. Now, there's something that I haven't included in this drawing, and it's my fault. I need to start doing it. Technically, how many electrons does oxygen have going around it? It has 1 and... So technically, it's 2 partial negatives. Does that make sense? Because it's got 1 from this one, and it's got 1 from this one. So technically, it's got 2 extra electrons circling it. Okay. So, Stakeesh, which end of the hydrogen or oxygen is going to be surrounded the K? Why is it oxygen? Yeah, this is the negative, and this is the positive, so we need to match those up. Okay. So, now, it said no more than how many waters? I'm just going to put 3 around each one of them. And again, I know that's only 6, but it says no more than 10, so we're good there. All right, so oxygen is going to go like this. Now, you can do this. I mean, it doesn't... I think it's stupid to have to draw the little bubbles anyways. But personally, this is exactly how I would do it. And I might even potentially go as far as doing this. I would say that oxygen is 2 partial negatives and the hydrogen is a partial positive. That way they know what the heck you're talking about. So let me ask you this. Does this drawing represent arrangement and proper orientation? How many of you knew this now that I've told you? Right? I've done this a ton of times. Let me ask you this. How many of you would have done this? Well, let me see if this will work. I'm almost willing to bet that most of you would have gotten this right. How many of you would have done this? Most of you would have done this right here. Right? Every single one of you, not realizing it, but like, this makes sense, right? It's surrounded by water. But does that adhere to proper orientation? How many of you would have done that? Just be honest. Most of you probably... And it's getting you thinking. It's getting you thinking of what's actually happening. Yes, this is kind of correct. This is something I would expect an honors person to do. You guys need to step it up just a notch. You've got to be able to know this. Now, what am I going to do around the I? Very good. It's going to be the H's attached. And I'm not going to draw the bubbles around it. That just takes way too much time. But you guys get the point. Okay, so it's the proper orientation. Any questions on this? Now, I did not give this to you on the test because I have a feeling every single one of you probably would have missed a few points. And so I don't want to do this. The first time you saw this, I wanted this to be something that I was doing for you and showing you how to get through it. So my expectations would not have been too high. You'll learn how to do this through me teaching you how to do it. So when you get on the day of the exam, you're like, oh, I remember how to do this because I've seen it, I've done it, I've practiced it. Okay, let me show you the key so you can see what the key would have looked like. So you can see where your points come from. All right, so if you'll notice, the sketch should clearly show, and again, most of you would have probably got 2 points. You probably would not have got the third one. A clear representation of at least one K ion, at least one iodine ion separated from each other, with it labeled and charged. We probably all would have gotten that one, right? That one was pretty easy to do. Each ion surrounded by at least 2 water molecules. If you would have put H2O, would you have got that point? Yeah, you would have. But this is where the third one would have been. You probably would not have got this. The water molecules with a proper orientation around each ion. Hence, the oxygen end of the water closer to the potassium and the hydrogen end closer to the iodide. Did we do that? Again, you probably would have gotten those. But the third one would have been where you lost it. So again, 1 point. Each point is earned correctly drawn, label, particulate representations. Now, this is where I wanted to make sure. This is what I want to show you. Representations that include more than one formula unit are acceptable as long as at least one of them had separated into ions. So in that beaker, what if you had drawn this and you left it together? Would that have been okay? As long as somewhere else, at least one of them was what? Separated. So you would have been okay. As long as you show at least one. So you see how they're not going to kill you if you add a solid? They're still going to give you some points. So I just wanted you to see that as well. The next one 1 point is earned for correctly drawn picture of the water molecules. Again, that would have just been water around it. And the last one was for the proper polarity or the orientation. Okay. Any questions on that right there? All right. Now, let's flip on the back. Let me just show you this. Part A, I kind of made a mistake. You really don't need a balanced equation. And that is going to be from part, that right there will be part C and D, so you don't need this. But it says 75 milliliters of CO2 at that pressure and that temperature were involved. How many grams of CO were produced? What was that bullet number 2 I said? Look for PIV inert. So PV equals nRT. Now let me ask you this. If we have PIV inert and it asks for grams, what are you going to be solving for? N. What is N again? N is moles. So it's PV over RT, right? Here's the thing you have to realize. No. First of all, what do you have to do to milliliters? Change it to liters, and this is the one some of you would not have got. That. Let me talk about this first. What is the value for R? .0821 in the unit. Very good. Liters times atmospheres over moles times Kelvin. Now, we changed the liters, right? This is the one that would have gotten you. Millimeters of mercury and atmosphere. That's the one that probably would have caught you up. This is what you need to know. In 1 ATM, there are 760 millimeters of mercury. So how could I convert that to atmospheres? Millimeters of mercury is on top. Where's that have to go? I always want you to think about this. No, that's not moles. That's ATMs. Sorry. So you would just divide. And whatever that number is, just plug it into this formula for P. And the rest of it you can kind of solve. Oh, one last thing. What does T always have to be in? Get that into Kelvin as well. So just add what to it? 273. So yes, you got to change all of those. And the rest of it, don't worry about. Okay. We're running out of time because of the long-winded fire drill. I do want to cover that one other sheet real quick. It's got a little bit more pertinent information in it. two things. Two things. Number one, once I got to looking at it, that one's almost impossible. It's up here as well. It's right there. Okay. And then number one, for some reason, I don't like it either. It's a pain in the butt problem to do. So what I want to do is I want to scroll this down and I want to do number 2 because I want to show you how it works. Okay, so what's your first rule whenever you're doing redox? Find the zero. Are there any zeros in this one? HG, very good. So this is 0. What is this? -1. This is +2. All right, so let's figure out what mercury does first. So mercury goes from 0. This is going to be equal to -1, -2. What makes that true? +2, and so that is. So what did mercury go through? It went from 0 to +1. All right. Guys, what I'm going to do is during my lunch, I'm going to finish this up. I'm going to keep recording, and I'll send it out to you just as a, if you will get up with people in second period, I think they're doing a study session at Dakota tonight at 5:30 if y'all want to join them. Okay. Okay, to pick this topic back up. So remember, we're doing redox reactions here. So we've just determined that mercury, if you will follow along with me real quick, mercury goes from 0 to a +1. So you know that is oxidation. Now, manganese, it's going to have to be the opposite. Notice another thing, that chlorine goes from -1 to -1. Now, it did not change oxidation states. However, because it did change states of matter, it must be in the net ionic. And here's what I mean. This is an aqueous, right? Because it's an ion. But over here, this is a solid. And how we know this is a solid is the solubility rules. Remember, all chlorides are soluble unless they're with heavy metal bad guys. And guess what? Mercury is one of those heavy metal bad guys, so it is a solid. Now, manganese, set this equal to 0, -2, -4, so this is a +4. So if you will notice, manganese goes from a +4 to a +2, so that is reduction. So now we have our design, we have our setup. We have our red cat OA and our ox and raw. All right, so reduction. MnO2 goes to Mn2+. All right, and the other one. Now, this is when you have to really pay attention. You have to really pay what's going to go on here. And here's what's happening. Since mercury and chlorine, or really the chloride ion, are on the right in this solid, you have to include both of them on the left and their ion and their elemental state. So that's why it's got to look like this. Again, since they are both here, let me change that color so you can see it. Since they're both here, they both have to be on this side because, you know, it's not hydrogen, it's not oxygen, so we can't balance them. So since they're together in a compound, they have to be on the opposite side as well. Now, the top one. We have one Mn, and then 2 O's. Well, we know since this is an acidic solution, we can balance using waters. Now, specifically, we need 2 waters. Okay, now since we have hydrogen, since it's acidic, we need to add 4 H pluses. Now, since this is acidic solution, 4 H pluses because we're an acidic. Since we're in the reduction side, remember, we need to put the electrons on the reactants. Reduction and reactants, they go together. So this whole side is a +2. This whole side, those of you need to remember, this 4 applies to this plus sign. This is a +4. Okay, so to balance it, I need 2 electrons. On the bottom, the only thing that's not balanced is the atoms. So let's do that. So I need 2 Hg's, 2 Cl minuses. So we don't need any hydrogens, we don't need any water, so we're good there. Now, since we are in oxidation, our electrons go on the other side. Now, this whole side is neutral. This whole side, remember, those of you that keep messing this up, that 2 does apply to that negative, so it's -2. So that means I need plus 2 electrons. So remember, this is something important. We always balance for atoms. We always balance for charge. And then we always balance our electrons. Now, if you'll notice, if you go through and look, double check this. Our atoms are balanced. The top one is a positive 2 on the left, positive 2 on the right. Our oxidation is a negative 2 on the left, negative 2 on the right. So that balances. And notice this one. We have 2 electrons here, 2 electrons here. So our electrons also balance. So we're done there. So the only thing remaining that we have to do is add our 2 half reactions together. Remember, what's on the left stays on the left, what's on the right stays on the right. So we have 4 H pluses plus MnO2 plus 2 HGs plus 2 Cl minuses. And we have Mn2 plus 2 waters plus mercury chloride, Hg2, Cl2, and that is it. Okay, so if you notice, really the only thing that changed from the original equation to the final equation is the hydrogen ion and the water. And this is simply because you're in an acidic solution. And what does a solution mean? You got to have water. Since it's acidic, you got to have the hydrogen ion. So that is that problem right there. Okay, so I'm going to move on to the other side. All right, let's look at this one. Remember, first rule when you're doing redox, look for your zeros. Well, this is a 0, and that was an easy one. Zinc goes from 0 to plus 2. So think for just a second. Tell me in your head what that would be. That would be oxidation. So let's go ahead and set this up. And again, guys, I promise that this red Catoa, Ox, and Rob, this will come in huge in this next chapter we're fixing to do. No, this is Ox and Raw, okay? And electrochem. Okay, so we now have our 0 to positive 2. We said what's oxidation. All right, so zinc goes from this to Zn2 plus. Now, there's no hydrogens, there's no oxygens. They're already balanced. The only thing we need is, since we're on oxidation, remember the electrons go on the other side. So plus 2 electrons. Now, this is the one where it gets to be a little pain in the butt. So now, please, 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 please look at your exceptions. In this case, hydrogen is going to be a negative, let me change the color. It's going to be a positive 1. Set this equal to 0. Let me double check this. Okay, I went ahead and worked this out. To be quite honest with you, this one kind of confuses me, and here's why. Anytime hydrogen is with a metal, it is a negative 1, which is what this version would be. However, arsenic is a metalloid, so I'm not quite sure what hydrogen would be. So worked it out both ways. But regardless of the fact, this is what I want you to grasp, that arsenic over here is a guaranteed plus 5. I did the math here. But here it is a negative 3, and here is it a positive 3. So regardless of the fact, whichever one, it is going to reduce. We know that as a fact. So we don't have to really think about that as that one is that at all. I am leaning towards this being the case. And the reason why is because hydrogen's a plus 1 here, so it needs to be a plus 1 here. So that's what this is what I'm going to lean of what you actually see. So I do think that one is incorrect. Okay, so let's go through and finish this up. So we have H3 ASO4 going to go to ASH3. So now I'm going to need some waters. So I need 4 H2Os. Well, that just gave me 3 plus 8 hydrogen. So 3 plus 8 is 11. And I already have 3. So that means I just need 8 H pluses. Okay. So total charge on the left is neutral. Total charge on the right is 8 positive. So I need 8 electrons. Now we need to balance those electrons. So multiply the whole bottom by 4. That way it'll give me 8. And please do not forget, you got to add your half reactions. Okay? All right. So we're going to have 8 H pluses plus H3 AsO4 plus Zn. It's going to go to As H3 plus 4 H2Os plus Zn 2 plus. Okay, so we have, let's see, 12 H's, 12 H's, 1 As, 1 As. We've got 4 oxygens, 1 zinc, 1 zinc. Totally, guys, I messed this up, sorry. Remember, you've got to distribute this as well. So there needs to be a 4 here and a 4 here. Now this makes sense. You have 8 total pluses on the left and then 8 total pluses on the right. Okay, I'm glad I double checked that one. Make sure you get your 4s in there. All right, so hopefully this has helped. Again, go through the test objectives. Make sure you're prepared. Make sure you look through everything. Please look through the explanations. You're going to see those as well. If you have any questions, email me. I think some of you are doing a study session tonight, so if y'all need any help, just come see me tomorrow morning if you need anything prior to that. You'll have a good day.